Michio Kaku, what is the theory of everything?
The theory of everything is what drives hundreds of physicists around the world. And it could be the crowning achievement of 2,000 years of our investigation into the nature of matter. We want an equation, 1 inch long, that will allow us to, quote, read the mind of God. We want an equation that will summarize everything we know about the universe. Gravity, light, the electromagnetic force, the nuclear force. We want all of it into a single equation, which will give us not just the Big Bang, the formation of planets and galaxies, but even the formation of people, maybe even love. All of it in a theory that eluded Einstein for the last 30 years of his life. And today, we think we have it.
We do.
Yeah?
Why do we think that?
Because we have a theory called string theory. It is fantastic. It is incredible. It has astounded the world of mathematics and physics. And now you can't move in the physics world without bumping into somebody who wants to talk about the 10th dimension, the 11th dimension, the multiverse, hyperspace, time travel. All the things that were once considered science fiction are now centerpiece in our understanding of the nature of everything.
You called it a theory, however.
It's a theory because we are going to test it with the Large Hadron Collider. You know that Big Bang machine outside Geneva, Switzerland, that some people think is going to tear the world apart? Wrong. It's a machine of science. And we hope to create a mini Big Bang by slamming protons together near the speed of light, recreate a teeny-weeny bit of Genesis, and from that, extract information that will show us that perhaps string theory really is a theory of everything. And that's what I do for a living. That's my day job.
Where did string theory come from, and who's the founder of it?
You're not going to believe this. In science, we always say that you make observations, you have a theory, you go make more observations, and it's a very, very tedious process. Wrong. Nobody that I know of in my field uses the so-called scientific method. In our field, it's by the seat of your pants. It's leaps of logic. It's guesswork. And in 1968, string theory was found by accident. Two postdocs, Veneziano and Suzuki, were looking through a math book, and came up with the beta function, which seemed to describe the collision of pi mesons. Why should a math book describe the intricacies of the collision of subatomic particles? Years later, we found out that it was a vibrating string that made all these things possible. What I did was, me and my colleague created a field theory of strings. What I did was I created an equation 1 inch long that will allow us to summarize all of string theory, all the equations of string theory. Now it's this huge, gigantic theory, hundreds of people working on it, and we hope to describe the results from the Large Hadron Collider outside Geneva, Switzerland, a $10 billion machine dedicated to unraveling the secret of nature itself.
What is that formula?
Well, everybody knows E equals mc squared. That equation is 1 inch long, and that's the secret of the stars. Matter, energy, they convert into each other, and that's why the stars shine at night. That's why we have the energy that lights up the universe. But Einstein was not satisfied with the theory of just energy. He wanted a theory of everything. Gravity, the electromagnetic force, all the forces wrapped up into a single equation. And then some people ask me, well, so what? I mean, can you get better color television this way? Can you get better cable reception? And the answer is, in some sense, yes. It is a theory of everything. When Newton unraveled the force of gravity, that gave us a mechanics, which gave us the Industrial Revolution. So the Industrial Revolution, in part, was set off by the discovery of the laws of gravity. Then Edison, Maxwell, Faraday worked out the laws of electricity and magnetism. And that gave us lasers and computers and the electric age. And then Einstein and others helped to work out the nuclear force, which lights up the stars. Now, we want a theory of everything, a theory of all forces. We want to create a superforce. And what did this superforce create? The universe itself. It is the driving force of creation. It's the energy of the Big Bang itself, the superforce.
Dr. Kaku, is Isaac Newton still relevant today?
Very definitely. Every time we launch a space probe and we send a space probe right past the rings of Saturn, right past Uranus and Neptune, you wonder, how do we do it? How do we send a space probe so close we could go whizzing right by the rings of Saturn, which is billions of miles away? And these are the laws of Isaac Newton, the laws you see around you that make skyscrapers possible, steam engines, locomotives, rocket ships. All of that is due to Isaac Newton. And then when you start to go near the speed of light, and you start to get exotic things like black holes and expanding universes, then you need the laws of Einstein. But even that's not enough, because once you approach the beginning of the universe, Einstein's equations break down. So at the Big Bang, Newton is out the window, Einstein is out the window, and at the Big Bang, we need a theory of a superforce, and that we think is superstring theory.
Is the theory of relativity fact?
Yes, it should not be called the theory of relativity. It's a law. Every time we accelerate particles near the speed of light, they never break the light barrier. Einstein is the cop on the block. You realize that relativity has been tested more than the traffic laws that we find in our neighborhood cities. Every time we launch a satellite, every time we shoot radio into outer space, every time we use a GPS, it all comes down to Einstein's theory of relativity. It's a law, not a theory.
Michio Kaku, in your book Hyperspace, you write, all physical knowledge at the fundamental level is contained in two pillars of physics, general relativity and the quantum theory. Einstein was the founder of the first, was the godfather of the second, and paved the way for the possible unification of both. What is quantum physics?
If you were to summarize all physical knowledge, I mean everything, the whole shooting match, lasers, microwaves, gases, liquids, everything into two great theories, they would be the theory of relativity, which gives us black holes and big bangs, the theory of the big. And then we have the theory of the small, that is atomic physics, which gives us laser beams, transistors, the internet. All the electronic wonders that we see around us are consequences of this quantum theory. The irony is, and this is the fundamental problem rocking all of physics, these two theories don't like each other. The theory of the big and the theory of the small hate each other. Every time you try to combine them, it's like a shotgun marriage. It never works. And this is where string theory comes in. String theory is the only theory in all the decades we've worked on this that actually merge these two into a single theory. It's amazing. They just like zip, form one coherent framework. Now, some people say, well, maybe I don't like string theory. Maybe I want another theory. Well, hey, there is none. This is the only game in town. No other theory has been able to combine the theory of the big, relativity, with the theory of the small, the quantum theory, into a single theory. This is the only game in town. So I tell young people, if you don't like it, create your own theory.
Is your job to disprove string theory?
No, my job is to put it into its final form. That is, it was discovered by accident in 1968, and we've been discovering all its secrets slowly, year by year. The theory is smarter than us. We were, in some sense, not supposed to see this theory for maybe another 100 years. The theory is so advanced, and it fell into our lap accidentally, that we're just dazzled by the sophistication of the mathematics. Mathematicians have been shocked, absolutely shocked by the mathematics coming out of this theory. So my job is to put in its final form. When we have it in its final form, then we can start to compare it with the electrons, protons, neutrons that we see around us.
In Visions, Dr. Kaku, you write, the quantum theory is the most ridiculous theory ever proposed in the history of science, flying in the face of all common sense and intuition. The quantum theory opens the door to all sorts of sticky paradoxes which defy all our notions about the universe. The quantum theory has only one thing going for it. It is unquestionably correct. It has survived every experimental challenge hurled at it. Is it controversial in your world?
The quantum theory is only controversial when you talk to philosophers, theologians, and the average person. To a physicist, it's accurate to 1 part in 10 billion. We can take an atom, shine a laser beam at it, And I can predict the properties to 1 part in 10 billion. The consequences are the internet, GPS, laser beams, computers, fiber optics, a broadband internet. All of that is a consequence of the quantum theory. Now, you'd think that a theory that powerful would be logical, compelling, and intuitive. Wrong. It is the most bizarre theory ever proposed in the history of science. Einstein couldn't get his head around it. It reduces everything to probability so that there's a probability that electrons can vanish, reappear someplace else. Electrons can be 2 places at the same time and exist in multiple states at the same time. Now, that's stupid. I mean, how can you possibly exist 2 places at the same time? How can you be in multiple states simultaneously? Well, get used to it. That's just the way the atomic world is. So why don't I vanish and reappear someplace else, like on Mars or the Moon? There is a probability that I'll do that. In fact, we give our PhD students at our college a question. Calculate the probability that you will vanish and wind up on the planet Mars. Give me a number. It turns out you have to wait longer than the lifetime of the universe for that to happen, but it's a calculable number. This is insane. This is absolutely counterintuitive. But the problem is, it's right. That's how our world is constructed. Our world is stranger than you realize at the atomic level. Now, we don't see it because we average out all these bizarre quantum effects. We're large objects. We consist of a lot of atoms. But at the atomic level, electrons exist in multiple states all the time. And you know what that's called? That's called the laser beam.
Good afternoon, and welcome to Book TV's In-Depth program. This is our monthly program where we feature one author and his or her body of work. This month, it's physicist and author Michio Kaku from the City College of New York. He is the author of about 8 books, 6 of which are readable. The others are textbooks, and unless you're an advanced student in physics, I'm not sure that they would apply here. But if you would like to call in and talk with Dr. Kaku, here are the numbers. 202 is the area code. If you live in the East or Central time zone, 737-0001 is the number for you to call. Those of you in the Mountain and Pacific time zones, 202-737-0002. You can also send us an email at booktv@cspan.org. We will be live with Dr. Kaku for the next 3 hours. Doctor, you write in your book Hyperspace. First of all, what is hyperspace?
Hyperspace is dimensions beyond the visible universe. Everybody knows the universe is expanding. But then the question is, what is the universe expanding into? The universe, we think, is expanding into another dimension. So think of a balloon. If you have a bug on a balloon, the bug would say, well, my balloon is expanding. I can measure the rate at which the balloon expands. But then you ask the bug, well, what are you expanding into? And the bug will say, I don't know. The balloon is all there is. The universe is the balloon. So what is a balloon expanding into? Well, obviously the 3rd dimension. We think our balloon is expanding into 11-dimensional hyperspace. Now, get your head around that. We're way beyond the 4th dimension. We think that the instant of creation was basically a quantum fluctuation in 11-dimensional hyperspace.
Why 11?
It turns out if you construct a universe of 13, 15 dimensions, the universe is mathematically unstable. The mathematics shows that these universes topple down to 11 dimensions. You can't escape it. String theory is the only theory which selects its own dimensionality. You can write Newton's laws in any dimension you want. You can write Einstein's equation in any dimension you want. But why do we exist in 3 dimensions? For the first time in history, we now have a theory which actually selects its own dimensionality, because these other dimensions are unstable. And then 11 dimensions, we think, and today we think we have it.
We do?
Yeah.
Why do we think that?
Because we have a theory called string theory. It is fantastic. It is incredible. It has astounded the world of mathematics and physics. We want all of it into a single equation, which will give us not just the Big Bang, the formation of planets and galaxies, but even the formation of people, maybe even love. All of it in a theory that eluded Einstein for the last 30 years of his life. We want an equation 1 inch long that will allow us to, quote, read the mind of God. We want an equation that will summarize everything we know about the universe. Gravity, light, the electromagnetic force, the nuclear force.
Michio Kaku, what is the theory of everything?
The theory of everything is what drives hundreds of physicists around the world. And it could be the crowning achievement of 2,000 years of our investigation into the nature of matter. And now you can't move in the physics world without bumping into somebody who wants to talk about the 10th dimension, the 11th dimension, the multiverse, hyperspace, time travel. All the things that were once considered science fiction are now centerpiece in our